Stormy night here. Hopefully the Wi-Fi doesn't cut out. Quick review of systems before we cover the two laws of thermodynamics that you need to know for ESS. So again, an open system exchanges both energy and matter with other systems. And these are basically every system that we're going to encounter in this class. It could include a person, a farm, a community, ecosystem, a cell, scalable to many different levels. A closed system is going to be one that exchanges energy but does not exchange matter. So as we talked about with Biosphere 2, right, those people were locked in to that system. So it was effectively closed, at least for some period of time. And then we discussed the Earth as well, largely closed, except for, some asteroids and things like that. And then, of course, an isolated system would exchange neither energy nor matter with other systems. Basically just the universe, at least as we understand it currently. So these open systems exchange energy and matter, but that still leaves the question, where is all this energy and matter coming from? So for example, if you plant an acorn, within a few decades, you'll have a giant oak tree in the same place. But where did the wood come from that makes the oak tree? Where did the leaves come from that make the oak tree? They're not in the acorn originally, so how did they actually get there? So that's our first law of thermodynamics, of course, as we talked about. Energy and matter cannot be created or destroyed, just transferred or transformed. So that acorn was transforming sunlight energy and water energy, carbon dioxide, nutrients into, of course, the bark and the leaves and everything else that it makes. And then we saw this when we were doing our systems diagrams as well. All of the energy going into these systems must equal the energy coming out of the systems because the energy can't disappear or anything like that. And then same in this system, all the sunlight, solar radiation coming into the Earth. The term for solar radiation is actually insolation. That's all has to equal the amount of solar radiation or long wave radiation, heat radiation leaving the Earth. And then you also could see that in the Silver Springs diagram that we looked at way back the very first week of class. Where all of this insolation, the sunlight, must eventually equal all of the other outputs in the system. So if you were feeling exceedingly bored, maybe you actually could add up all these values to see if it actually matches. So the second law of thermodynamics is a little bit trickier than the first law. So we could look at my computer, which I'm using right now as a system. So I have my computer plugged into the wall. And so from the wall, there's electricity coming from Arizona power supply, which uses a lot of hydroelectric power from dams, also some coal power, also some natural gas. So that's all transformed into electricity, which then runs through my power cable and then into my computer. So that way it's fully charged. So then the question is there any energy that's leaving the system, right? Seems like this is pretty closed, right? Electricity just coming through here, going through my charging cord and then to my computer. So how is this an open system? So if you touch the box right here, mine's actually quite warm right now. And that's because some of that electricity actually just gets turned into heat, which is not as useful of energy, right? I can't charge my computer with heat. Otherwise, I could just go set it in the sun and it would be totally charged. I can use the heat to warm my feet, which is kind of nice, but that's not super useful overall. But the second law of thermodynamics is basically this, telling right here that we always lose some amount of energy in whatever kind of system we have. So the official wording of the second law of thermodynamics is one that I think trips people up a lot. So the official wording is just that the entropy or disorder in an isolated system will always increase. And so what that really means is that no system is going to be 100% efficient because it's always going to use that, it's always going to lose energy through heat dissipation, whether through friction, through respiration and breathing, through movement, etc. So entropy is this idea of disorder. And so the original law is that like disorder always increases, right? We're always going to get less useful energy. So if we go back to our computer here, right, we start with really useful electricity. We can use this electricity for lots of different things. And thankfully, most of the electricity goes into my computer. But a lot of the electricity actually becomes heat, right? This is actually entropy, disorder that's leaving the system. I can't use this heat energy anymore. So that's the second law of thermodynamics right there. And actually, as I unplug my computer and close that system, or at least disrupt that connection, you might notice that your computer actually gets hot too. So you are still losing energy that way. And entropy continues to increase. So the way we really see this in ecology is through something called the 10% rule. So you actually can see that inefficiency right here, right? And we see all that energy getting lost at each level of this food chain. So we start here with primary producers having lots and lots of energy, which they get from the sun. But then as they're consumed by grasshoppers and other primary consumers, they only are able to receive a certain percentage of that energy. And that's just because the plant is using that energy for lots of other things, right? The plant is actually also using respiration in its cells. And so it's using energy from that. And so not all of that energy actually gets transferred into plant tissue, which is what the grasshopper is eating. And same thing for the grasshopper, right? He ate all that plant and he's trying to grow big and strong, but he's also hopping around trying not to get eaten. And he's also breathing and using energy that way. So the energy that he ate from the plant doesn't all go into building muscle, into building flesh, right? Some of that energy is wasted. And so that's why when he gets eaten by a mouse, the mouse only gets a small fraction of that total energy. And the same thing happens, right? Mice have a really high metabolism. They're moving really quickly and their heart rate is super fast and they have really, really warm temperatures. So there's tons of heat energy just going out of this mouse. And so that's all energy from the grasshopper that's just getting wasted. And that energy from the grasshopper, of course, originally was from the plant, which was originally from the sun, which if you took big history was originally from nuclear fusion in stars, originally from the Big Bang, going back all the way. But basically, this is how you should think about the second law of thermodynamics in ESS, in ecology, right? We're losing energy at each trophic level, and then we're not going to be 100% efficient. So if we go back to our Silver Springs diagram, you actually might notice that we start with really wide arrows here with lots of energy from the sun. And then as we move into the plants, these arrows actually get more and more narrow, and the number values get narrow as well. So we got the herbivores here, even smaller, carnivores there, even smaller, until you get just very, very small little arrows there. And then these are all getting smaller because so much of this energy just ends up coming over here, right? Community respiration. This is the second law of thermodynamics right in this picture.